Architecture in Algebra 2 by Jake Yurachek, Andy Nguyen, and Ethan Bowie. Jake Yurachek, who's doing Chapter 6 in the audio, Andy Nguyen, who's doing Chapter 7 and the technology, and Ethan Bowie, who's doing Chapter 8 and the director. Chapter 6, Using Nth Roots in Problem Solving. Using nth roots in problem solving is often used to design and construct buildings and other structures in the modern world today. Architects use nth roots to solve problems for all types of projects, ranging from determining the necessary weight of a building to determining the necessary water flow for building a dam on a river. For example, a formula is needed to regulate the water flow for a dam on a river. The flow rate Q in cubic feet per second can be calculated using the formula Q equals 3.367 LH raised to the 3/2, where L is length in feet of the bottom of the spillway, and H is depth in feet of water on the spillway. An architect needs to know the flow rate of the dam with a spillway that is 20 feet long and has a depth of 5 feet. First, plug in the length and depth to get the formula Q equals 3.367 times 20 times 5. Raise the answer to the power of 3/2 to get Q equals 336.7 raised to the 3/2. Conclude with a flow rate of 6,178.24 cubic feet per second. Architects often use these formulas not just for river dams, but for all kinds of other construction projects. Chapter 7, Exponential and Logarithmic Functions. Architects sometimes use exponential and logarithmic functions to calculate how far apart 2 points on a structure are, how curved the side of a building is, and the highest point of an arc. By using logarithms and exponential formulas, an architect's life can be made much easier. For example, the height y in feet of an arc an architect is designing can be modeled by the function y equals 646.6 minus 52.74 times e raised to the x over 96.6 plus e raised to the negative x over 96.6, where x is the horizontal distance in feet from the center of the arc. The architect needs to know the maximum height of an arc, and by using an exponential functions involving e, the architect can conclude that the maximum height of an arc is about 541.12 feet. So with the help of these functions, an architect can speed through his work. Chapter 8, Model, Inverse, and Joint Variation. In the world of designing and constructing structures, architects often use inverse and joint variations to calculate the specifications of their materials for their buildings. In this way, they can figure out what their dimensions must be to get the result they want. For example, the load P in pounds that can safely support by a horizontal beam varies jointly with the beam's width W and the square of its depth D, and inversely with its unsupported length L. The equation is P equals A times W times D raised to the 2 over L. A is the constant. An architect needs to know how they can modify the beam so it can support 4 times the original weight. There are multiple ways that an architect can solve this problem. 1. Multiply the width by 4 to get P equals A times 4W times D raised to the 2 over L. Multiply the depth by 2 to get P equals A times W times 2D raised to the 2 over L. Or double all the dimensions to come up with P equals A times 2W times 2D raised to the 2 over 2L. Architects can use these kind of equations that include inverse and joint variation to determine how they must change their dimensions of the wood in order to achieve the desired weight the beam can safely support. In conclusion, as hard as it may be to believe, Algebra 2 is always being used by someone. Architects use Algebra 2 all the time, from evaluating nth roots and using rational exponents to modeling inverse and joint variation. So the next time you're stuck on a tough problem and complain to yourself, when will I ever use this? Remember this presentation and the countless other ones you've had the pleasure of hearing.